So let's take a look at advanced limits. So for number 1, we have this limit as x approaches pi from the positive direction of sine of 1 over x minus pi. So obviously, when we direct substitute pi into the equation, we just get sine of 1 over pi minus pi, which is 0. And that's basically, we cannot define something divided by 0 here. So that doesn't work. But the biggest hint that this problem is giving us is as x approaches pi from the positive direction. So let's think about a number very close to pi, but just maybe a millionth of a fraction or a billionth of a fraction above pi. So that, let's say we get sine of, or sorry, not sine. Let's say we just look at this denominator here. Let's pick an x value that's so close to pi, just a tad bit above it. So let's say x is equal to pi plus like a millionth or a billionth of a fraction above it. If we take that and subtract pi, we'll get an answer of like 0.000001 repeating. You know, it goes on forever. That's basically so close to 0. And when you plug that back into the equation here, 1 over a very small fraction like 0.001 is basically going to get you to infinity depending on how many zeros you have. So then when we say the limit as x approaches pi from the positive direction of sine of infinity, well, if you think about sine of infinity, sine is an oscillating graph. So it does not exist because of oscillation. So it does not exist because it will oscillate forever. So looking at number 2, we have the limit as x approaches infinity of 1 plus 3 over x raised to the x power. So when I direct substitute infinity in the equation, I get 1 plus 3 over infinity raised to the infinity power. 3 over infinity is basically 0, and 0 plus 1 is 1. So we end up getting 1 to the infinity power. And that's basically indeterminate. So we cannot, because 1 to infinity can be basically anything. So instead we have to go back and sort of manipulate the equation so that we can change it and use L'Hopital's rule. So we know that the limit of this function is going to equal a certain value. So we can set this equal to a constant, c. So now what I can do is natural log both sides of the equation. So as a limit as x approaches infinity of the natural log of 1 plus 3 over x raised to the x power equals the natural log of c. And I'm going to step away from the limit and the natural log of c for a second, just so I can focus on the natural log of 1 plus 3 over x raised to the x. Because now what I can do, using properties of logs, is bring this x down in front of the natural log. So I can have the x times the natural log of 1 plus 3 over x. So now what I can do is move the x to the denominator, because then I'll get natural log of 1 plus 3 over x over 1 over x. So now if I include my limit again, so I have the limit as x approaches infinity of the natural log over 1 over x. Now let's say I plug in infinity to both sides, the top numerator and the denominator. I'll get the natural log of 1 plus 3 over infinity, which is 0, over 1 over infinity. The natural log of 1 plus 0 is the natural log of 1, and the natural log of 1 is obviously 0, and 1 over infinity is 0. And here's my indeterminate form of 0 over 0. So now when you have this kind of form, you can use L'Hopital's rule. So I'm going to go back to this equation here and take the derivative of the top and the derivative of the bottom. So the derivative of natural log of u is just u prime over u. So we're going to take the derivative of this over 1 plus 3 over x. So the derivative of 1 plus 3 over x So I'll write just the derivative 1 plus 3 over x. The 1 is just a constant, and derivative of a constant is 0. So I can rewrite 3 over x as 3x to the negative first, and by using the power rule, we get negative 3x to the negative second power. And the derivative of 1 over x, so let's say I write this down here, I can rewrite it as x to the negative first. Or I'll put the derivative sign, so d over dx of x to the negative first. Once again, we use the power rule, negative 1 times x to the negative second. So if I were to rewrite this equation here, we have the limit as x approaches infinity of the derivative of the top, which is the u prime, and we found u prime to be negative 3 x to the negative second, so we get negative 3 x to the negative second, divided by just 1 plus 3 over x, because remember the derivative of natural log is u prime over u. Now divide that by the derivative of the denominator, and the derivative of 1 over x is negative x to the negative second power. Now if I were to simplify this, if I divide by negative x to the negative second, I'm basically multiplying by the reciprocal. So we get negative 3x to the negative second over 1 plus 3 over x multiplied by 1 over negative x to the negative second. Obviously the negatives will cancel and the x to the negative seconds will cancel. So what we're left with is 3 over 1 plus 3 to the x. And now I'm going to rewrite the limit as x approaches infinity, 3 over 1 plus 3 over x. And now I can direct substitute infinity, because what I'll get is 3 over 1 plus 3 over infinity. 3 over infinity is basically 0. So we get 3 over 1 plus 0, which is 3 over 1, which is 3. And this is actually not the final answer, because remember in the beginning we set it equal to c, and we have it equal to natural log of c when we natural log both sides. So we have to set 3 equal to the natural log of c. And to find what c equals, or to find what that number equals, we have to get rid of the natural log, and the only way to do that is by raising both sides by e. We get e to the 3 equals e to the ln of c. E cubed stays on the left side, and e to the natural log just cancels, and we get c. So this is the limit. So looking at number 3, we have the limit as x approaches infinity of the natural log of x minus the square root of x. Now, there's no way to actually move anything to the numerator or denominator to use L'Hopital's rule at first, but I think the most effective way to manipulate this equation is by first factoring out the natural log of x. So if I were to factor out natural log of x, I get 1 minus the square root of x over the natural log of x. And since there's a multiplication, or let me just add a times sign here. If there's a multiplication sign here, we can actually split this into two different limits. So we have the limit as x approaches infinity of the natural log of x multiplied by the limit as x approaches infinity of 1 minus the square root of x over the natural log of x. Now looking at the limit as x approaches infinity of natural log of x, this one's pretty easy, because when you just plug in infinity, the natural log of infinity is just infinity. So that side's done. So now we have to look at this side here, where we have the 1 minus square root of x over the natural log of x. So because there's a minus here, I can split the limits up. So we have the limit as x approaches infinity of 1 minus the limit as x approaches infinity of the square root of infinity, or sorry, not the square root of infinity, not yet, the square root of x over natural log of x. The limit as x approaches infinity of 1 is just going to stay 1. It's never going to change. So this is just equal to 1. And then if we were to plug in infinity into the equation here, or the limit, we would get the square root of infinity over the natural log of infinity. The square root of infinity is infinity, and the natural log of infinity, as mentioned before, is infinity. And so here's our indeterminate form. So now we can go back to this limit and use L'Hopital's rule. So if I were to scroll down just a second, square root of x over the natural log of x. So if I were to derive this, or derive the top and derive the bottom, and use L'Hopital's rule, the derivative of the square root of x is x to the 1/2, so we can use the power rule, where we bring the power to the front and subtract the power by 1. So you get 1/2 x to the negative 1/2. And the derivative of the natural log of x is just 1 over x. So if I were to put these two back together, I'll get 1 over 2 times the square root of x divided by 1 over x. Dividing by 1 over x is the same thing as multiplying by x. So when I do 1 over 2 times the square root of x multiplied by x, I'll get x over 2 times the square root of x. So I'm going to include my limit again. So the limit as x approaches infinity of x over 2. I'm actually going to rewrite the square root of x as x to the 1/2, because now you'll see that we have x to the first on top and x to the 1/2 on the bottom. So this function is actually top heavy, and when the function is top heavy and you plug in infinity, the function will diverge to infinity. So now I can take what I found here, what I found with the limit as x approaches infinity of 1 and the natural log of infinity, and plug it in all together. So I get infinity. Remember that it's 1 minus the natural log, or 1 minus square root of x over the natural log of x. So I get infinity times 1 minus the limit of the square root of x over ln x, which is just infinity, like we found here. So 1 minus infinity is negative infinity. So we have infinity times negative infinity, which just equals negative infinity. And that's our final answer.